friends, colleagues, students. We are extremely pleased to have Professor Frank Kelly to deliver IAS speak today. Frank Kelly is professor of the mathematics of systems in the University of Cambridge. He was elected as a fellow of the Royal Society in 1989 and a foreign member of the National Academy of Engineering at US in 2012. In 2013, he was awarded commander of the Order of the British Emperor, so 大英帝国勋章 the Chinese know better. Okay. Without further ado, let's welcome Professor Frank Kelly to deliver the speech. Okay. Thank you. By the way, I'm also Frank. I'm Frank Chen from Management Science, the College of Business. So please make sure you don't ask me, you ask this Frank. Okay.
I view myself as a mathematical scientist interested in applying mathematics to various areas, particularly areas that are not the traditional realm of applied maths. They're not physical applications. They tend to be applications to technological systems, humanly constructed systems of one type or another, telephone networks, the internet, traffic networks, things that we have constructed, but which have a level of complexity that begins to approach that of large-scale physical systems. So the kind of methods that were developed by mathematical scientists, physicists, mathematicians to describe statistical mechanics, to describe phase transitions in magnets, or to describe freezing or boiling of water, those sorts of methods where lots of particles or lots of individual elements are interacting. Those sorts of things now are a major part of the systems that we design, and trying to understand them seems to me to be a very interesting challenge. So that's the sort of thing I'm interested in. And so quite a lot of my work has had applications to things like networks of communication networks, interactions of the queues, the way packets queue within a network. But this particular area has that same infrastructure underneath it, the same mathematical infrastructure of trying to model interacting queues, but it arises from a quite different application. In fact, my interest in this area, I suppose, began, I've always had a layman's interest in it, but the real interest began just after the 2008-2009 financial crash. At that time, economists were, how should I put this? This is an interdisciplinary science group, so I should just... So economists tend to be very confident of their subject, and for a period just after 2008 and 2009, they were not quite so confident. They're almost as confident as physicists are, right? But in the period after the financial crash, they kind of opened up and invited lots of people from other disciplines. And I was invited to a few meetings where the aim was to try to explain how instabilities arise in other technological systems. So instabilities in telephony networks or in the internet or whatever, with the possibility that there might be some crossover, that might give some intuition as to the instabilities that were arising in the economic system. And indeed, I think there are there are similarities there, and there are things that read across, although there are many, many things that are different. So I got kind of interested in the area at that time, and in particular the questions about how you regulate markets and models for understanding what would be the impact of regulatory structures upon financial markets seems to me to be a really interesting thing, and something where potentially mathematical scientists can contribute. So that's what sort of interested me in it. The particular model that I'm going to describe today here is absolutely not something that would be of any use to a trader who was trying to make money in a market. The aim of the model is not to model precisely the fine detail which would allow you from day to day or hour to hour to make money. The aim is instead to model things at a level of simplicity where you can get some sort of analytical tractability and where you can comprehend what's going on, with the aim being to understand, suppose you were to change the rules of the market, suppose you were to change the way that the system is designed, what would be the consequence of that change? There are players playing within the market, buying and selling, and if you change the rules, then their strategies will change, and the new equilibrium that arises will be a consequence of the equilibrium of the game that they're playing. So, it's not enough to say, I don't like this behavior, let's forbid it, because as soon as you change the rule of the game like that, then you will necessarily change the strategies of the players. And so the new equilibrium they move to may well be one that's worse than the one you started with. I mean, this is very familiar in models of road traffic, where we understand very well that reducing the capacity, say, for example, increasing the capacity of a particular road within a road network may well be counterproductive. It may well make everyone's delay worse. That's well understood. So similarly, in these sorts of situations, understanding what the impact on the equilibrium of the system is to change rules is not obvious. And so the model is an attempt to get a simple model that's got that one can use for insight and to understand that sort of thing. So that's background. So let me just start. This will be an overview of the talk. I'll start with the introduction, go through various the results that I have. Oh, I should have said this is joint work with Elena Yudovina, who was my PhD student, then went to be a postdoc at the University of Minnesota, and we wrote the paper that this talk is based on while she was there. And she's now left the university position to join a tech company in Minnesota, and I'm sure you'll hear more of Elena in one form or another later in life. She's a very able person. Right, so this is the overview of the talk, and I'll start with just the introduction. So a limit order book is a trading mechanism for a single commodity market. So it's of great interest. It's a model of price formation. Price is the economic notion of a price is formed somehow. The price emerges from some operational behavior of individuals, and this is the model of price formation. And it's used in many, many financial markets. There's a huge amount of literature on it, and quite a large amount of that literature is involved with analyzing or checking models against the very large amount of data that is collected. Just imagine the data that's collected from a stock market, for example. So our aim is an analytically tractable model, and we're particularly interested in a highly traded market where there may be many, many operations of buying and selling on a very fast time scale, and certainly a faster time scale than, for example, anything changes concerning the fundamentals of the stock that's being bought. So in that case, you might hope to find some sort of separation of time scales where there's a separation between the things that are driven by the high-frequency matching of supply and demand from things that are driven by changes in the fundamental value of the share or the stock. There's a huge amount of previous work, but particularly relevant to the model I'm going to describe is the work listed here. So Stigler and Lukoc first described the form of model we're going to describe here. Stigler was an economist and won the Nobel Prize a little bit later for some of his work on regulation, amongst other things. The later papers here are the particular feature that's important of these papers that shares with what we're going to describe here is that they concern Markov models, and so they're attempting to analyze a system using the same mathematical technology. And this is just a small sample of all the papers that are out there. Okay, so let's now describe the basic model of a limit order book. So if you imagine that prices are discrete, we'll look at both cases, discrete and continuous. But if they were discrete, then a typical system state would look like this. So we have bids here. So there's one bid there, two bids, three bids at these prices. And these are orders to sell. And because along the bottom here is price, and because these people want to sell at a price that's higher than the price that these want to buy, these don't get matched. Right? He's asking for too much. This bid's asking for too much relative to what people are offering to pay. But they can wait there to see if anyone else arrives that's willing to make a deal. So what might that look like? Well, if an arriving bid, this bid here, is lower than all the asks present, as this one is, then it just joins on there. It's just added to the limit order book. If an arriving ask is lower than a bid present, as this one is, then what do you think will happen to that? So that ask will come, and it'll take one of these. The one it'll take will be this one. So what it'll do is it'll take that one. So that arriving ask is matched to the highest bid. So our assumptions for the model will be that unit bids and unit asks arrive as independent Poisson processes of unit rate, and we'll assume that the prices associated with bids, respectively asks, are IID random variables with given densities. So this is an enormous simplification. We're looking at a situation where what's going on is driven by independent Poisson streams, IID variables, and there's not a change. These densities here are constant. They're not varying over time. Right? And our idea is that we're looking at a fine time scale where the fundamentals aren't changing. So the limit order book at time t is the set of bids and asks with their prices. So those earlier examples I gave were of a discrete limit order book. We'll move backwards and forwards fairly rapidly or without comment between discrete and continuous. Here, these densities then are for the continuous case, but you could see the specialization to a discrete case. Now, the assumptions, IID and Poisson, mean that the limit order book is a Markov process. I don't need to know anything else about the past of the limit order book other than the current state in order to predict the future. So our underlying idea is the following, that the long-term investors place orders for reasons exogenous to the model and view the market as effectively efficient. So I'm imagining that the long-term investors might be things like pension funds or asset managers, where they have their own reasons for wanting to buy and sell shares. They maybe try to work out their own view of what the fundamentals are, or they need to rebalance their portfolio because they've taken on a new set of pension liabilities or whatever. And so they come to the market and they view the market as effectively efficient. So they're prepared to declare to the market truthfully what the price is that they value it at. And if it clears at that price, fine, and if it doesn't, it doesn't. And we assume that there's a high volume market with substantial trading activity, even over time periods when no new information is available on the fundamentals of the asset. And that will then lead to a timescale separation. So later on, much later in the talk, we'll add high-frequency traders. And the high-frequency traders are at the opposite end of the spectrum. They don't have a view our model of a high-frequency trader will be someone that has no view at all about the fundamentals, but does observe very closely the limit order book and observes it in real time and can act extremely quickly. So what we're proposing then is that rather than the real world has got traders that are across the spectrum from the long-term investor that has a clear view of fundamentals and views the market as efficient, through to the high-frequency trader that has no view of the fundamentals, observes things at a very high frequency and acts very quickly. In reality, there's a mixed spectrum all the way between them. But our mathematical simplification is to say, let's see what happens if we just suppose that the traders are in two groups at the two ends of this spectrum. What will happen then? So that's the way we're attempting to analyze it. And I'll maybe comment on this, or we can discuss this a bit later at the end. The hope of the model, it's no more than the hope at the moment, is that by analyzing what happens for a mixture of these two extreme types of trader, you get some insight into what might happen with a spectrum. Okay, so if you were to so this is the earlier thing was just a diagram to explain a limit order book. This is an example of what happens if you simulate a limit order book with a finite number of bins. I think there were 50 bins here and uniform arrivals over those 50 bins. So this is the position of the limit order book after a long time. What happens if you simulate it? You get some insight. What happens is that this bit here down at the extreme left wanders up and up and up and up, and down here wanders up and up and up and up. So these are asks that are too high and bids that are too low, and they don't seem to clear. They seem to just build up here. Then on the other hand, what goes on down here is that it seems to not grow. What goes on in the middle here doesn't seem to grow. So the major result that we'll do later, and spend some time getting to it, is to just make that statement precise. Right? So that's kind of a simulation of what we see happening and an overview of what we're going to get around to proving. Right, so two-sided queues arise in many circumstances. And so one of the motivations for looking at what we're doing, I've described before. I'm trying to understand models for regulation. But another motivation is that two-sided queues arise all over the place nowadays, and they're enabled by modern technology. So let me just give a kind of extreme example. Once upon a time, you could model taxis in Cambridge, the city I come from. You could model taxis as a two-sided queue. There was one place you could get taxis outside the station. There were two queues there. There was a queue of taxis and a queue of passengers. And one or other was usually empty, and it fluctuated. Now, a very simple model of that would be suppose that taxis and passengers arrive as Poisson streams of the same rate. Now, in that circumstance, the number of passengers minus the number of taxis, so one queue will be empty, but so this passengers minus taxis is positive or negative according to whether the queue is of passengers or the queue is of taxis. Then that, under the assumption of Poisson arrivals, would be what? I could get the audience to wake up by asking them the question. What? It would be a random walk. It would be a simple symmetric random walk. Now, a simple symmetric random walk is one of the simplest things you meet in probability theory, and the simple symmetric random walk is a null recurrent random walk. It returns to zero infinitely often, but the mean time between returns to zero is infinite. So even though it's a very simple Markov process, to describe, its behavior is quite subtle, right? It's not transient, it's recurrent, but it's null recurrent, so the mean time to recur is infinite. Now then, that is nowadays being replaced in cities by, instead of a two-sided queue at one location, it's been replaced by a distributed queue. If you imagine, for example, Uber, then what's happening is you're getting taxis you're getting passengers that pop up in space. And the taxis are distributed in space, and the queue has to be matched. You have to decide which taxi to match with which customer. And information and communications technology is pushing this in all sorts of areas. Once upon a time, supply and demand could be caricatured as follows. Supply and demand demand is, for example, a superposition of lots and lots of individual choices, but we're looking at such an aggregated system that demand looks like a continuous curve with price. So the demand curve might look like a smooth, continuous curve, and so mathematically that would make sense for aggregations of very large numbers because of the law of large numbers. If it's a single market, a single price clearing supply and demand, then you've got two smooth curves which intersect at the price where the market clears. Well, more and more markets don't look like that. More and more markets look like they're highly differentiated in space and time, and that what is being matched at a much more granular level, right, as the taxis and passengers are being matched here. Or as A or B and B, or as whatever. The matching looks much more granular. Now, when it becomes much more granular, there are many, many, many stochastic features that become important, because the law of large numbers is not there to help you, obviously. I mean, that is, it may help you, but it's not obvious how it helps you, because what's going on is so granular that the stochastic effects are potentially predominant. So two-sided queues arise in all sorts of different areas now, and these two-sided queues are large numbers of queues where there are many things that have to be, many matchings that have to go on. So maybe the matching that arises from this microscopic matching at the granular level, maybe there are some regularities that arise in it, but you can see that if there are regularities that arise in it, we're going to have to work to get them. It's going to be like the regularities that arise in large-scale physical systems where we deduce phase transitions from microscopic models. So you know, there's work to be done here. One of the features that's kind of interesting about the limit order book is that while it's very complex in some sense, you know, these rules, the price being continuous, it's very complicated in that sense. There's one thing about the limit order book that is very simple. The matching rule is obvious because the label on a bid or an ask is the the totally ordered real number, then when I match, I know which one I match with. As soon as you move to these other examples, then in general there's two issues. First of all, what's the strategy for matching? And then, given a particular strategy, what are the stochastic dynamics of the system? So, for example, for waiting lists for organ transplants, there's a complicated matching rule depending upon histocompatibility. Donors and recipients have histocompatibility, and how do you match them? If you've got certain positions. So sometimes that matching question is perhaps the most predominant question, but at least in the limit order book, it's straightforward. We know what the matching rule is. So the question is then, what are the dynamics? Okay, so what are our results then? So the motivation, the two motivations for what we're doing. One is to try and get a simple model that helps in regulatory discussion, but another is that one wants to kind of push forward the mathematical infrastructure that you use to analyze two-sided queues. And this looks like a good example case to try and understand, because if we can get some methods that work here, maybe there's a chance then of extending them to other two-sided queues. So what are our results? Well, the first results we're going to describe concern thresholds. There exists a threshold, kappa b, with the following property. For any price x that's less than that threshold, there is a finite time after which no arriving bids less than x are ever matched. So at that left-hand end of the simulation, for any x less than a threshold, there does come a time when no arriving bid less than x is ever matched. So that's not a stopping time. We don't know when we get to that time, but if you had the privilege of observing the infinite future, then there would be a finite time after which no arriving bids less than x are ever matched. And for any x greater than that threshold, the event that there are no bids greater than x in the limit order book is recurrent. That means it keeps happening. However late you wait in time, there'll always be a time later when there are no bids greater than x. So it looks like there is a threshold there that the behavior in the long term of bids that arrive to the left of the threshold is they don't get cleared, and to the right, they all get cleared. And similarly, with the direction of inequality reversed, there exists a corresponding threshold for asks. So the intuition here is that eventually the highest bid and the lowest ask evolve within this interval here, where we put a minus epsilon and a plus epsilon to capture the fact that these are strict here. Okay. So for any epsilon, eventually the highest bid and the lowest ask evolve within that interval. That's the first result we'll get, and I'll describe how we prove that. That's pretty simple to prove, relatively simple to prove that one. Now, our second result is the following. There's a density pi ax, respectively pi b, that's supported on this interval between the two thresholds that gives the limiting distribution of the lowest ask and the highest bid in the limit order book. And these densities, pi a and pi b, can be solved for, and they solve these equations here. Right? So, to prove this is going to be quite hard, but the equations themselves are relatively straightforward to write down. The intuition behind these equations is as follows. Suppose I look at the right-hand side of equation 1a. Then that's the probability flux that the highest bid in the limit order book is at x, because that's pi bx, and that it is matched by an arriving ask with a price less than x. So that's the probability that an arriving ask has a price less than x. Right. To match it, it has to be less than x, and that's the density of the arriving asks, and so this integral here gives us the probability that an arriving ask will match that one there. Now, on the other hand, the left-hand side is the probability flux that the lowest ask in the limit order book is more than x, so that's the integral from x up to there of pi a. So that's the probability that the lowest ask is more than x, and then that's the density that an arriving bid enters at price x. So these are the probability fluxes at which a bid becomes the highest bid or stops being the highest bid. So it's the flux into and out of that position of the highest bid. So you know, if provided one's got enough recurrence in the system, right? Speaking casually for the moment, provided one's got enough ability to establish recurrence, then this is what you'd expect to be true. Now, just a word here for Markov chain aficionados, right? So normally with Markov chains, suppose you've got a discrete state Markov chain, countable or finite, then if I can write down a probability distribution that solves the stationary equations, solves the equilibrium equations, then that's a proof that the process is positive recurrent and that solution is the stationary distribution, the limiting distribution, the equilibrium distribution. Right? Observe here that the position, this pi ax and pi bx, are not stationary distributions for a Markov process. The highest ask and the lowest bid is a projection down of the Markov state. The Markov state is the entire limit order book, and so that the highest bid and the lowest ask are projections from a very high dimensional Markov state, the limit order book, to a very low dimensional state, one value, the highest bid. And there's no theorem that tells you that if I've got a probability distribution that satisfies the equivalent of the equilibrium equations, but for a projection of the Markov chain, that there's anything going on for the, you can't deduce any recurrence from that. And you can see that from very simple examples. If I just imagine, you could exercise for those that, for the Markov chain people, just give a very simple example where you've got say a transient Markov chain, but where a projection of it is or is not satisfy equilibrium equations. Right. Okay. So those are the two major results. So let's just illustrate it with an example. Suppose that I take densities that are uniform on 0, 1. So all prices are confined to the interval 0 to 1, and arrivals and of asks and bids are both uniform on that. Then in that case, we can solve the equations beforehand. We can solve them in any case, but the solution here is this very explicit form here, where kappa is this, and W is the unique solution of this equation here. Observe that any example with FA equals FB can be reduced to this, provided the density of asks and bids is the same. Then our model is invariant under a monotone transformation. We can just stretch the stretch the price axis so that it becomes uniform on 0, 1. Right? You can transform any continuous random variable. I can construct as an image of a uniform random variable, just to find the inverse of the distribution function. So similarly here, this example here, any example where FA is equal to FB can be reduced to this example by a monotone transformation. Okay, so this for that example, this is the density of the highest bid. So we can just work it out here. And this is for the binned model with 50 bins and a continuous model. So the continuous model you see as this dotted line, and the binned model you see as the step function here. And you see this here, there's a shoulder bin here, where in fact the binned model is averaging over from the continuous model. There's the shoulder bin there has this interesting behavior here. I mention particularly binned and continuous models because that's an important part of the whole proof technique. Okay. Right, so let's now move on to a proof overview. So this will be a rough overview of the proof. I'll just go through the various steps of it and the important features of that. So first of all, for thresholds, a key result is monotonicity. And the monotonicity result will be important for the relationship between binned and continuous models. So suppose that a bid is added. Suppose I take the limit order book, right? And now I just add a bid. And suppose I let the original limit order book evolve with the arrival processes of bids and the arrival processes of asks. And I put those same arrival processes of bids and asks into this new limit order book, which has had one bid added. Right? So these are coupled. These two limit order books start off with the states being the same except for one additional bid in one of them. And then they're subject to the same processes of arriving bids and asks. Then what's the difference later on between these two limit order books? Well, the future evolution of the limit order book differs by either the addition of one bid or the removal of one ask. And if a bid is shifted to the right, in the future evolution of the limit order book, the number of bids to the left of x is not increased for any x. So there's a straightforward monotonicity result. If you just think about what happens if I add a bid, then it might cancel an ask in the book already, or it might cancel an ask that's about to arrive in the book. Right? And it might also be cleared rather than another bid. Right? Those are the two things that can happen. But both of those things cause the limit order book to be ordered relative to the other one as follows. Right? Right, so the limit order book differs by either the addition of one bid or the removal of one ask. Now, where are the differences? And if a bid is shifted to the right, in the future evolution of the limit order book, the number of bids to the left of x is not increased for any x. So those things are easy. The way to prove those is just induction. Right? Imagine those things are true for the first arrival or the first the first arrival of an ask or a bid. Prove it's true then, and then just deduce by induction that every subsequent arrival of an ask or a bid leaves these statements true. So that monotonicity is rather neat because it lets me get a connection between the binned model and the continuous model. If I imagine a continuous model, yes, then I can turn that into at least two binned models. Right? If I take the continuous model, I could just look at the bins and shift everything to the left-hand end of its bin. Shift all the asks to the left-hand end, all the bids to the right-hand end. Or I could take the original thing, look at the bin model, and shift them in the other direction. And what the monotonicity result gives me is that the continuous model is bounded between these two. So if I can analyze the discrete bin model, right, then I can analyze a model. The continuous model, I don't need to explicitly analyze itself because I can bound it between two binned models where the difference between the continuous model and the binned model is simply the shift to the left or the right. So rather than a continuous price, a real variable, say between 0 and 1, I could look at not a real variable, but a variable that is a decimal place truncated to 10 decimal places. Right? Okay, it doesn't look very different, and mathematically that's the epsilon. Right? I can get as close as I like to the behavior of the continuous model by binned models, which are as close as I like. So that's a key feature. Now then, look at this. For each x, by Kolmogorov's 0-1 law, the event that finitely many bids will depart from prices less than or equal to x has probability 0 or 1. If you just think of this, that's a statement about the tail sigma field of the process, and so it's got probability 0 or 1. So I can define the threshold kappa b to be the supremum of the x such that that probability is 1, and similarly define the threshold kappa a using asks. So the result about thresholds is relatively straightforward, although it's using quite a profound result. The difficulty and the main part of the proof is not that. The main part is the following. Despite the existence of the thresholds kappa b and kappa a, it does not follow that the interval kappa b minus kappa a is ever empty of both bids and asks simultaneously. We know that it's empty of asks recurrently. We know it's empty of bids recurrently, but we don't know that it's empty of both together. Let me just think of a way to describe that. No, okay, I'll think of a way to describe it a bit later. So to establish the existence of the limiting densities that the second result claimed, the major challenge is to establish positive recurrence of the binned models. We have to establish positive recurrence because from the positive recurrence we can then deduce that various limits exist. The intuitive argument I gave you earlier is enough to prove the result, provided you know that limits of various forms exist. But there's no reason why limits of various forms might exist. If I think of the model, then if I were to ignore price, then it is the null recurrent. If I just look at the number of bids that have arrived minus the number of asks, that's the null recurrent simple symmetric random walk. So there's something deeply null recurrent going on underlying all this. So positive recurrence is not at all obvious that there is positive recurrence in the system. So that's the major challenge here. So the way we do that is as follows. So it's a technology, a kind of mathematical technology that's been developed in the queuing network area over many years with many contributing authors, and particularly Bramson and Williams and Jim Dye and various other people have shown how you can rescale queue sizes and use that to relate the behavior of a stochastic process to fluid models. And if the fluid models have particular features, particularly that they converge to being empty, then from that you can deduce results about the stochastic process. So the way we prove this is that all the fluid limits tend to 0 in finite times for bins inside this critical interval. And that's the hard step. And the reason it's hard, and the step that within our results, I'm not going to go through this in fine detail because it's excruciatingly difficult to do. It takes pages and pages to do. And the bit that's hard is that the evolution of the queues depends on which are positive. Now, in most of the applications of fluid limits earlier, the evolution of the queues depends upon which are large. But the particular matching rule we've got means that which ones are positive is critical for where flows are in and out. So positive or not is the key thing that affects the drive, and that's what makes that hard. So we could deduce from that the binned limit order book is positive recurrent, and then the continuous limit order book, as I described earlier from the monotonicity result, the continuous limit order book is bounded by binned models. Right. So suppose so this is kind of formally the result that gives the equations I wrote earlier. Suppose the densities are bounded above and below, then the highest bids and lowest asks have densities denoted by pi b and pi a. It's easier to write down these equations here, not for pi b and pi a, but for scaled versions of them. So if we just look at these scaled versions here of pi b and pi a, then the thresholds satisfy these results here. This here has to be equal to that because bids and asks leave in pairs, right? So the long run rate at which a bid is met has to be equal to the long run rate at which an ask is met. And so that has to necessarily equal to that. And the distribution of the highest bid is such that the scaled density here is the unique solution to this ordinary differential equation. So you'll see that this ordinary differential equation here has got two derivatives, one there and one there. So it's a second order equation here. And if you look back at that, so that earlier set of two equations I gave is intuitively easy to comprehend. And we did that intuition. But if you look at the two equations, first of all, there's two of them. And secondly, they're an integral equation. They're not a derivative. They're an integral equation. Now, if you imagine differentiating those two integral equations, you would then get two linked differential equations. They're each first-order equations, but because they're linked, it gives you a second-order differential equation. So this here is the same thing as those earlier two equations. It's just that the second-order derivatives are turned into two first-order integral equations. Does that make sense? Yep. So they are just restatements. The intuition is easier to describe with the integral equation, but the ODE theory is better for derivatives.
That condition may not hold if there is unilateral cancel of order or bit order.
Unilateral cancel.
Yeah.
So
it's not in pair. They may not disappear in pair.
So unilateral meaning that it reneges or it leaves. Yeah. Yes, that's right. That's right. So our model did not. Okay, it's interesting. But I should say this: that our model had that an arriving bid or an arriving ask enters is either cleared or it enters the book. That's it. It doesn't later leave, other than if it's met. And so cancellation is not allowed in our model, and we'll come back to discuss that a bit later. And I think we'll. Right. So these ordinary differential equations have got initial conditions, and they need to have sufficient conditions, and these are sufficient conditions to give unique solution to the boundary. The boundary conditions here give a unique solution to this equation here. Okay, so that's the proof overview, and what I'm going to do now is describe a few extensions and a few things that begin to use the model. The orders we've considered so far, each with a price attached, are limit orders. Market orders are requests to be filled immediately at the best available price. So market orders don't have a price attached to them. They just say, I want to buy. Whatever price you're prepared to give me, I want to buy. So we can model them straightforwardly by just assuming that x is between 0 and 1. We've seen that any prices can be mapped back to that and associate a price of 1 or 0 with a market bid or a market ask. So this differs from our earlier model in that we now have atoms. We now have potentially atoms. Nonetheless, the earlier equations, the two sets, generalized to this. So here we see here, so mu A here is market orders arriving. So they're like at 0. Mu A is the arrival rate now of the limit orders. And so these two things here have to be added together. And similarly over here, mu B is the arrival rate of market bids. And so that's like those market bids are all arriving at 1. So it's like there are atoms in these distributions, but at the extreme points of 0 and 1. And the model here has got, you can see a kind of generalization. I've put in these parameters, nu A, nu B, because we need parameters in order to balance the ratio of market orders to limit orders. So I need the extra parameters because I've got to give that balance between market orders and limit orders. Right, so those equations generalize to this, although now the existence of a solution is not assured. So let's just look a bit more closely at an example of that. So suppose that we look at the uniform example, but it differs now in that a proportion lambda of orders are market orders. So it's the same model as the uniform example earlier, except that now we suppose that a proportion lambda of orders are market orders. Then, provided lambda is less than this parameter w, 0.278, whoops, sorry, then the limiting distribution for the highest bid is this thing here. So pi b is our earlier solution. Pi b is the earlier solution. And what's going on here is that in this case here, where a proportion lambda of orders are market orders, what's happened is that the earlier density is scaled. We just stretch it a bit further. So observe, this here is a linear transformation of x, right? So what happens is that you just stretch out the earlier density so that rather than extending from kappa b to kappa a, it extends from kappa lambda to 1 minus kappa lambda. So it just extends out on a stretched axis, where pi b is the earlier uniform solution and kappa lambda is this. So observe it's a convex combination of these terms here, or sorry, it's this linear transformation here of w over 1 plus w. So provided lambda is less than w, that's true. But what happens as lambda increases? Well, what happens as lambda increases is that pushes to the left and this pushes to the right. So that's going to cause a problem. But sorry, I've forgotten to note this. But so where lambda is less than w, there's a finite random time after which the order book always contains limit orders of both types and no market orders of either type. Hence, the earlier analysis applies. So provided lambda is less than w, the analysis applies. You just have that the limit order book evolves on a slightly wider interval, right? But what happens when lambda is greater than w? If lambda is greater than w, then the problem is that this interval extends to hit 0 and 1, to hit either 0 or 1. Or both in the symmetric case. If lambda is greater than w, then infinitely often there will be no asks in the order book, and infinitely often there will be no bids in the order book with probability 1. So the difference between the number of bids and asks in the limit book is a simple symmetric random walk and hence null recurrent. So we can deduce that there will infinitely often be periods when the state of the order book contains limit orders of both types and no market orders of either types. But such states can't be positive recurrent. They can't be positive recurrent. So what's going on here is that if the proportion of limit order books is too high, then what's going to happen, if it's too high, is that what's going to happen is every now and then you're going to discover that you've lost a bid-ask spread. The proportion of market making, if the proportion of market orders goes above this threshold here, then what happens is infinitely often you'll lose either the left-hand end or the right-hand end of the bid-ask spread. Right? And to my mind, that's quite an interesting conclusion. If the market makers are not providing enough liquidity in the form of the limit orders, then you'll find that this rather disastrous from the point of view of the regulator thing happens, that the bid-ask spread disappears, or one end of it disappears. It's interesting that such a simple model can, in one sense, simple. It's hard to analyze mathematically, but it's a simple model. The fundamentals are not changing the underlying price. It's simply the matching between supply and demand that is driving this. Right. So the last section of what I'm going to talk about is trading strategies. So now let's suppose that we, as well as these orders that are coming in and going out from the fundamental investors, we now imagine that there are other people there. Let's call them high-frequency traders or technical traders or whatever. And so I'm going to analyze a few strategies that they might use. So the first one will be market making. So let's suppose that a market maker behaves as follows. Places an infinite number of bid, respectively ask orders at P, respectively Q, where P is less than Q, but they're both in the interval between the two thresholds. So I'm a market maker. I kind of know that this price is evolving on this interval. I'll place a huge number of bids at P and a huge number of asks at Q, and it'll keep bouncing up and down between P and Q, right? I know it keeps bouncing. If I don't do that, I know it keeps bouncing up and down between kappa A and kappa B. My results tell me that the price is fluctuating up and down between these two thresholds. So suppose I just come inside these thresholds at P and Q and place a large number of bids and a large number of asks, then I'll just keep making money, right? For every pair of a bid and ask matched, I'll make a profit Q minus P. Well, there's still a question, where should I place P and Q? The profit per bid and ask matched goes up as Q minus P increases. So as I make the gap between P and Q bigger, I make more money per match, but the matches happen less often. Right? I bounce against those things less often. So there's an interesting little optimization to do there. So for the uniform, and you can write down that, we've got the stationary distribution. We can work out the stationary distribution by exactly the same, just solving the equations with a different boundary condition for P and Q. The earlier second-order differential equation, the formula we had for the log in it, I can just repeat that. It's just a slightly different form if I change the boundary conditions from there to there, from the two kappas to P and Q. And from that, I can write down the optimization that trades off the profit here against the frequency that I make that profit. And if I do that, for the uniform case, the profit rate is maximized with P being this, and it gives a profit rate of about that per unit time. So that's quite interesting. That's one strategy. What about another? Well, a second strategy would be as follows. Suppose a trader immediately buys every bid that joins the limit order book at a price above Q, and every ask that joins the limit order book at a price below P. So we call this sniping. The market maker didn't need to have fast technology. He just placed a lot of bids in one place and a lot of asks in the other. Right? Now imagine someone that's got very fast technology. They can see the limit order book, and they're able to do the following. They see something enter the limit order book, and they're able to immediately hit it. By immediately, I mean before anyone else does. Right? So let's call that sniping. So suppose that a sniper buys every bid that joins at above P and every ask that joins below Q. Well, the effect on the limit order book of the sniping strategy is to ensure there are no queued bids above Q and no queued asks below P, because he's hitting them all. So for P less than Q, the set of bids and asks on PQ has the same distribution in the sniping and the market making model, right? The sniper is not vulnerable to prices under fundamentals changing, right? Because let's just leave that aside for the moment. But so there's a difference in that larger model, but in this model they're the same. But for P greater than Q, there are no queued orders of any kind in the interval QP, and they're all sniped up by the trader. Now, P greater than Q, so he's buying every ask that joins at prices below P. P greater than Q, it looks bizarre, that strategy, right? If I imagine the uniform case, then in some sense the fundamental fair value is a half. But this sniper that's with P greater than Q is buying stuff at prices which are greater than a half and selling stuff at prices which are less than a half. It's causing there to be no queued orders of any type in the interval QP. They're all sniped up by the trader. But it looks bizarre because he's buying stuff at higher than what we kind of, who know the statistics and know the model, is better than fair value, right? Fair value would be a half, say, for this. So it looks bizarre that you would ever want to do that. But what's very interesting about the model is that that turns out to be part of an important strategy. Okay. For the uniform case, the profit rate is maximized at 1 minus P equals Q equals this. So P greater than a half and gives a profit rate of this. So it's lower than the optimized profit rate with the market making strategy. Right? I mean, what's going on is that you're clearing out all the bids in an interval, and the rationale for what appears for to buy something at greater than a half doesn't look like a sensible strategy. In fact, it is a sensible strategy, because what's going on is it causes that interval to be empty. It means that there are not bids in that interval from other people that are going to match other bids that are outside the interval. And so the overall performance of your strategy is better. Not at all an obvious result that would be true, but it is true here. And it's easy to analyze these and to get these numbers. It's just a simple calculation from the stationary distributions that we've got. Because we've got an analytic stationary distribution, it's easy to calculate what happens under any of these cases and to optimize. It's a work of just a few lines to do it. Okay. Now then, of course, I might do a mixed strategy. I might place an infinite supply of bids at P and snipe every additional ask that lands at prices X less than P, and similarly for the acquisition of bids. So I might do both sniping and market making. And in that case, we've got two parameters to fix, capital P and little p. And for the uniform example, the optimal choice is to place an infinite bid at P equals a quarter, an infinite ask at this here, 3/4, and snipe all the orders that land at prices between them. And that gives an optimal profit rate which is higher than the other two. Perhaps it's more obvious here why you snipe all the bids in the middle. I snipe all the bids in the middle while any individual bid looks like I might lose money on that. By sniping them all, I make the other part of my strategy, the market making strategy, make more money. Right? Because I'm keeping the bid-ask spread quite wide. I'm keeping the bid-ask spread as wide as between a quarter and 3/4. And that means that my market-making strategy is making more money. This is the contour of what happens under the two things. So, if you want to try and analyze these behaviors, then it's not enough to ask, is this individual transaction profitable? What you have to ask is if I'm doing these transactions with this policy and the system's been driven by random arrivals of supply and demand, what is the net consequence for the strategy? Right. Okay. So I'm not for a moment suggesting that this model is what will drive a high-frequency trader to behave in a certain way. What they will do is they will backtest, analyze strategies by seeing how they behave with data. But they get to strategies like this. Right? Now, the situation they're looking at is much more complex. The dynamics of the system are much more complex than we've got in our model. However, these simple strategies come out of a simple model. Right? So if you ask, well, how do I understand where this behavior is coming from? You don't need a complex model to define, to get to these behaviors. A rather simple one will give it to you. Okay, so let's look at some other cases. So suppose that we've got competition. There's a sniper and a slower market maker. Observe, the sniper requires the technology to be able to do things very quickly, to hit an order as soon as it comes in. The market maker doesn't. He just places his orders in there and just sees what happens. So the natural model here is of a leader-follower game, where the slower market maker chooses his capital P, and then the sniper optimizes the sniper's performance given that, and where the leader presumes that the sniper will optimize his strategy, or alternatively observes what's going on in reality and observes the behavior of the sniper. So in either of those cases, you'll get a Stackelberg game, a leader-follower game, and you find that the profit rate of the market maker is 0.073 and the sniper 0.020. So the numbers here are the numbers for the uniform model. That's not intended to be realistic. It's a transform of the other ones. But it's nice to get these numbers because one can compare them between the different strategies and work out whether one's a bit higher or a bit lower than the others. So it's an interesting test. So between market makers or mixed strategies, suppose there's a competition between market makers or mixed strategies, well, at the Nash equilibrium, the traders compete away the bid-ask spread and all their profits. So that becomes the traditional economic model of Bertrand competition. Between snipers, the fastest wins and monopolizes the profit. Suppose you've got multiple snipers that are that are competing with one another. Then when a bid comes in that it wants to hit, one of them will hit it, the others will not. And indeed, what they'll do is they won't want to be placing market orders, because if they miss the one they're trying to get, they'll pick up another one. So what they'll be doing is placing limit orders. They'll place a limit order to hit exactly the thing that's in the book. And when they fail to hit the limit order in the book, they'll then need to cancel their order quickly before something else happens. So the model will endogenously describe a behavior where if there are, say, 10 snipers competing with one another, there'll be 10 bids that come in. One of them will succeed, and the other 9 will be almost immediately cancelled. So, and what happens if you do that is the fastest wins and monopolizes the profit. And that was one of the points in Michael Lewis's book, Flash Boys, that there's an incentive to build fast technology, a fast direct optical cable between, I think, Chicago and New York, so that you could be slightly faster and be the fastest sniper. Well, quite a lot of technology, quite a lot of money spent on this. The firm that did it pre-sold use of the optical fiber to the traders, which was just as well, because almost as soon as it was commissioned, it was beaten by microwave connections. So it was just as well for the person that built the optical fiber, because the technology was immediately superseded by a faster microwave technology. But anyway, but one of the regulatory responses to this has been to say, well, this is a wasted societal effort, this investment in optical. It cannot be of any societal value to have reactions measured in microseconds or faster. So surely this looks wasteful. And one of the proposals has been to replace the continuous time limit order book by a discrete time limit order book. You could, for example, have batch auctions where you operate the limit order book, but in discrete time, every 1/10 of a second, say. So I choose 1/10 of a second because it seems like 1/10 of a second is faster than could any human or news or fundamentals change. And yet 100 milliseconds is a very long time in internet time. So 100 milliseconds is far enough, is a time where you have no real difficulty and you don't have to co-locate your computers. You don't have to do anything like that. So one of the questions is what happens? We could look at this. If you replace the continuous market with frequent batch auctions, then the snipers must compete on price. But interestingly, at the Nash equilibrium, the combined profit rate is more than 2/3 of what it was in the continuous market. So most of the profit the snipers make remains in the case where you replace their continuous time market with a discrete time market. They're not making money, so whoever's making the most money is not making it solely because of this. If you replace the continuous market by a discrete one, more than 2/3 of the profit that's made by these strategies will remain. So it's a mistake to feel that what's going on is a consequence. The profits that have been made there are a consequence. And indeed, what's happened in the time since Michael Lewis's book has come out is that the competition between the high-frequency traders has intensified, and the profit levels of them have gone down to closer to kind of normal profit levels. It's no longer an obvious thing to enter into that business. Right, so there's several other game theoretic models where you can see what happens if you have competition between different subsets of various people. But I'll not go through any more of those now. I'll wrap up with just some conclusions. So what we've attempted to do is describe an analytically tractable model. The dynamics are driven by stochastic fluctuations between supply and demand. There's no need to explain to deduce the various strategies that we've got. We don't need to have a more complicated model than that. Fluctuations between supply and demand are enough to generate that complexity of behavior. So we've used the model to analyze various strategies and the effect of competition in continuous and discrete time. So if people want to read more about this, it'll appear in Maths of Operations Research, but it's on the archive already. And I'll stop there, and thank you all for your attention.
Yeah, I'm Nanchen from Chinese University of Hong Kong. It's my great pleasure to be here and serve as a discussant to this great paper. I actually enjoy reading pretty much. That reminds me of the old years with David Yao in my first year of PhD study. I worked with him on queuing networks, so I read a lot of paper from you about bandwidth sharing. Okay, so I still remember my stuff. And afterwards, of course, my interest sort of drift away to finance or financial engineering. Anyway, let me recap the paper a little bit, and then I point out several places I'm interested trigger discussion. So this paper, I think, makes a very nice, remarkable theoretical contribution to understanding the so-called continuous double auction market, especially how it explains how the bid-ask spread can be formed over time. And there are two major points or major contributions from this paper. The first one is, as Professor Kelly mentioned during his talk, he and his co-authors successfully show or prove the existence of limited distributions for highest and lowest bid or ask price. And this is not very easy, as you can see through the proof sketch. And also, the work present integral equations or ODE to determine such kind of distribution density. Actually, the same idea has been circulated in the literature for a while. I noticed this paper written by Lukoc, published in 2003 in Quantitative Finance. Actually, I think this is also one of the major references of this book, this paper. So just the setup is as follows. So just thinking about there are two queues or two sequences of investors, say buyer and seller. And they walk in and they throw limit orders along this price line. They can put their limit orders at any level of this price line, okay, from the lowest 0 to the highest 1. And of course, the rule is very simple. The interaction rule is very simple, as mentioned by Professor Kelly. So if I'm buyer, say, if I pick up this price, if I find that before there's some guy sitting, there's some seller sitting, say, to my left, then we just pair up and then leave this system. And similar situation is for the potential, say, seller. Okay. So if you look at this system, you will immediately realize, oh, there should be 3 regions, right? The first, this left region, for those people, they submit very for those buyers, they submit a very low price. So it's very hard for them to find any matching from across from the sellers. Right? So as you can see, as time goes by, because they cannot be cancelled, the bids are so competitive, so the bids will steadily accumulate, and at the same time, you can see on this hand side, competitive asks will steadily accumulated over time. So what you can see, it looks like 2 impenetrable walls, say, building up. In these 2 regions. The really interesting thing, of course, should happen in the middle, because the arrival intensities of buyers and sellers are comparable, and therefore you can see recurrence situation for the queues in the middle. 5 minutes. Well, so. Based on that, you can write out your balance equations, so on and so forth. But of course, the first place, you need to answer the following question. Intuition is one thing, but how to carry out the mathematics is a totally different thing. So I think the major contribution of this paper, of course, is on that part, how we can carry out the calculation or the proof. And in Lukács' paper, he acknowledged that it is impossible. He claimed actually it is impossible to construct a self-contained evolution equation for this limit order book distribution. But of course, Professor Kelly's work completed this so-called mission impossible, because we have a so powerful tool in hand that is a fluid model and its limit. So we can. I just cite these equations from his paper, and you can see very, very clearly, or you can fully characterize the interaction between orders at different price levels. Okay, so especially from this equation, because I have time limit, so I just skip here. And also, some key techniques are involved. For instance, you are dealing with a continuous price model. You have to discretize it because you have so many variables involved. So that's why Professor Kelly introduced the so-called binned model. And also, there's a very nice connection between fluid model and the positive recurrence, the final target of this paper. And of course, that is a very nice contribution from him to set up this relationship for this specific model. I just want to add 2 comments or suggestions or discussion point to this paper. The first one is order cancellation, as Professor Ma pointed out. Actually, a lot of orders actually end up with being cancelled. So more than 97% according to ESA report. So I think that this cancellation feature actually is a very important factor for us to understand the limit order book shape. Of course, as you can see, in reality, you cannot see such kind of impenetrable walls building up right here. All these people will cancel out their orders because they just running out their patience. So I think my suggestion is that maybe it's possible for this model to incorporate such kind of feature, because we have so-called more. If I use analogy from queues, we have a lot of discussion in queuing theory about queues with abandonment. And in such a kind of literature, fluid limit or fluid model is still possible. So you just add more terms here, and maybe I think the major still, I mean, the argument maybe still can be carried out. I don't know. And 1 minute. So the second one is hyphen trader. I think this is also very interesting, because we can see how their interaction shape up the limit of the book or shape up the whole market. But there's an assumption assumed by this paper that these traders can take unlimited inventory. However, in practice, hyphen traders are typically very sensitive to this kind, to inventory level they can have, because they typically do intraday trading. So they have to, they want to get out the market at the end of each day. So if I add some, say, position constraint on the hyphen trading strategy discussed by you, then how the result in this paper will change? That is my question. Okay.
First, let me introduce myself. My name is John. I work as an assistant professor for finance. It's okay, I think my voice is enough. Teaching algo trading at the CTU, and my research field is exactly trading. And to be specific, it's called market microstructure. So today, it's a great pleasure for me to discuss Professor Kelly's paper. But before I get into the details, I'd like to provide some general intuition. In investment practice, there are in general two ways of doing it. One way is called bottom down, bottom up. The other way is called top down, right? So if you are doing top down investment, it means you look at like a country level macroeconomic stuff and then try to pick your portfolio. If you are doing bottom up investment, you look at the balance sheet, you look at firm fundamental information, right? So I feel like this is a pretty good analogy to what financial economists do versus what mathematicians do. Because mathematicians tend to do this kind of top-down research from very abstract, high-level models. While financial economists, we tend to do bottom-up analysis. We look at transaction data from NYSE. So nowadays it's about gigabytes a day. If you look at order level data, it's about terabytes a day. So it's huge. We also look at the very detailed transaction protocols, right? From different exchanges to see what kind of orders you can use. And from all these institutional details, we try to move up to make our model more abstract, more generalized, more tractable. But unfortunately, after reading Professor Kelly's paper, I found that the gap between Professor Kelly's top-down approach versus our bottom-up approach, it's still quite large. The gap
Spread is big.
Yeah. I think the gap can hold maybe Donald Trump's ego. So that's the reason maybe today I'm going to be a little bit critical about this paper, and I hope all of you won't mind. So first of all, I will provide...
people are very critical.
Yes, we are. It's a very competitive business. So I get grilled every time in conference. So the first part, I will do a simple summary, and then I will provide some comments on the model and some comments on the trading strategies, and in the end, I will conclude. So the summary is the model setup is a limit order book model with continuous price. This is a very fundamental feature in Professor Kelly's model. So limit orders arrive as independent Poisson process of unit rate, which makes sense. And the limit prices are IID random variables. And based on this kind of model design, the main result is an analytical solution of the limiting distribution of bid-ask spread. Okay, it's a tractable model, so it's a surprisingly a simple tractable model for a very complex limit order book market. And then Professor Kelly provided two high-frequency trading applications. The first is called sniping. The second one is, of course, market making. So let me first talk about the model. So the limit. So I always like to do this kind of a vertical thing, because if you look at the limit order book with trading systems, it's always like a vertical. So so the limiting distribution of a bid-ask spread looks like that. So that is actually in economics, that's cost of taking liquidity. Let's call it S. We can take it as equilibrium bid-ask spread in a limit order book market without market maker, without informed trader, without liquidity-driven traders. Because of that, we can call this model a limit order book model of noise trading. Okay? Because only noise traders are playing in the market. So what about let's bring in market makers? So market makers' contribution to the market is they provide a narrower spread for everyone else, which means they reduce the cost of taking liquidity to SMN. And because of that, their contribution to the market is simply S minus SMN, right? So they improve the liquidity condition of the market, and they make a gross profit for that contribution. Fair enough. But the issue about the economics of market makers' decision is a risk-return trade-off problem. Because if you think about that, if market makers, they set this SMM too wide, then they will lose competition, because another market maker with a narrower spread will win the trades. If, on the other hand, if they set this too low, then per round trip of trading, they only make a very small return, and that return cannot compensate the risk premiums required for doing that market making business. So what kind of risks are faced by market makers? The first one is called the inventory risk, because if you want to make a market, you have to always hold something, right, to preparing, selling to your customer. And you're holding a portfolio, and this portfolio has beta risk. So that's inventory risk. And we have models by Amihud and Mendelssohn in 1990. We have models from Ho and Stowe in 1981. The second risk is called adverse selection risk, which means if you trade with someone who has better information than you, so you get adverse selected. These kind of models are also very old. We have Kyle model in 1985. We have Gloston and Milgrove model also in that year. Okay, so in finance literature, people have considered this kind of within this kind of noisy trading model problems with these market makers like more than 30 years ago. In a competitive equilibrium, we can separate the spread provided by the market maker into three parts. The first part is the adverse selection risk premium. The second part is inventory risk premium. The last part is a reasonable optional operational cost. Right? They have to do this business. So we have a paper by Huang and Stowe published on the Review of Financial Studies in 1997 called The Components of Bid-Ask Spread, a General Approach. They designed an econometrical method to actually separate the three parts of the spread using actual data. All right? And this is a trend of the US equity market average effective spread along the years. We can see it's very low these days, okay? In NASDAQ, it's about 2.5 cents average spread. In MSE, it's about 1.5 cents. So the spread these days is very, very low. And then let me talk about the pricing of limit orders. The real-world limit order book market uses discrete pricing. The minimum price movement is called the tick size. For example, if SE has a tick size of 1 cent, and the limit orders are ranked following price and then time priority. So that means if the current bid is 10, the ask is 10.5 cents, then a new limit sell order at 10.4 cents, just 1 cent under the current ask, will undercut the current best ask and becomes the first ranked limit order. This is the price priority. But if a second limit order arrives at the same price, it will be ranked after the first one, and this is called the time priority. Okay, and this is a fundamental for a continuous limit order book. So continuously priced limit orders won't work in reality. I'd like to provide several reasons. The first one is, of course, time priority will collapse, because if price is continuous, you can submit a very small improvement in the price. So to be mathematical strict, for any epsilon greater than 0, bid plus epsilon or ask minus epsilon will undercut the best bid or ask, which means it will become an undercutting game for limit orders. You can, nobody wants to wait, right? You can always add or decrease the price just a little bit to become the first one, right? So the second reason is the trading data. This is more mechanical. The trading data will explode, because if you want the computer system to contain the trading data, and if you push epsilon close to 0, the size of limit order pricing data will go to infinite. All right? Imagine you have a price of 199,999 goes to infinite. The size of keeping this data will explode, and the exchange server will crash. Okay, so that's another reason why it won't work in reality. A more mathematical strict argument is that the real world market is run on the integer set. Okay, but the continuous limit order book runs on the real number set. And from our topology knowledge, we know these two sets are not homeomorphic. Right? So if you are talking about the limiting distribution, you want to make sure the problems are based on homeomorphic sets, right? So you can talk about limiting properties. A model that makes sense shows up in 2009, published on Journal of Financial Economics, called Informed Trader and Limit Order Markets by 3 professors from Chicago, Berkeley, and Michigan. They provide a numerical solution to a Markov perfect Bayesian equilibrium to a discrete limit order book. That is so far, I think, the best model deal with the limit order book market. But unfortunately, it's not an article. Actually, I saw their code, thousands of lines of C++ code to finish that simulation process. And then let me talk about the trading strategies. Sniping. Sniping is not a standalone high-frequency strategy, unfortunately. Sniping is one of the 2 legs of the arbitrage trade.
I think you will run out of time, so...
I think this is quite important, so please let me finish. In the paper, Professor Kelly cited the Bullish paper in 2015, published on Quarterly Journal of Economics. The example is about index arbitrage. So it's between S&P 500 ETF traded in New York and the related index future traded in Chicago, which means if the New York asset is overvalued against the Chicago asset, arbitrageurs will buy the undervalued one and short the overvalued one. So you sniping ask in one long order book, sniping bid in another order book. So unfortunately, sniping in one order book is nonsense, to be frank. And sniping in 2 order book is called arbitrage. That's Econ 101. Okay? And then let me talk about market making with infinite size. Professor Kelly already provided some comments on that. In reality, every trading account has a position limit. If you don't follow that, you are called a grog trader, right? Otherwise, the risk of getting run over is intolerable. I think Professor Kelly also mentioned that. So if you post infinite number of quantity on one side, market move up or down, you suffer an infinite amount of loss. So because of that, I'm skipping to that. I'm calling market making with infinite size is a highway to bankruptcy. So I think that is also another reason why this model is not so applicable to the real world. Now let's look at the actual data. Okay, this is the actual market depth at the bid and ask in NYSE. Okay, it's not infinite. It goes up and down. There are a lot of variation in it. And during crisis, the depth goes down because the market makers are afraid of doing business. And then please allow me to provide some interesting facts. So these days in NYSE, the timing is based on nanosecond. How short is that? About this much, all right? In a nanosecond, light only travels this distance. So it's very fancy high-tech. Secondly, current US equity market is highly fragmented. So you cannot really only consider $1 million book. If you want to do research on the market, it's multiple $1 million book. And the third one is, last year, Renesas Technologies filed a patent of order placement technology using atomic clock. The founder of this firm, a very successful hedge fund, is James Simons, successful mathematician, used to do differential geometry, and he's a former Cold War code breaker, former chairman of Stony Brook Math Department, and he left academia in 1977 to manage money. And his personal value is about $12 billion US. Okay, so that's how successful mathematicians moves to financial market if he really knows how to play, right? So I think time is up, right?
Thank you.
No problem.
For close comments, just like, I just, remind me something like this. When we review fundamental science, when we review the people from economics and finance, we reject. Probably, because they don't talk about our language. So they make assumptions we don't like. So clearly, this is the case. Professor Kelly's assumption, I feel comfortable with, but however, the economics, finance people feel, there's another.
But the reality is in economics and finance.
Okay, I answered. Okay, I read on my first, the second degree. I have a master in economics. I feel the economics, the models, they also make tons of unrealistic assumptions. Without those assumptions, can you feel the models? But anyway, my point is. That's Professor Kelly, the answer. That's.
I just have two small remarks to make. I suppose when we're teaching mathematics in Cambridge, there's very often the joke is made that we'll model the elephant by a point. And I suppose the other remark I should make is that in the mathematical sciences now, one of the major sources of funding for mathematics young graduates for fellowships, postdoctoral fellowships, and research centres is from James Simons, who's been a major supporter of mathematics. So we're very grateful to him for that.
Okay, thank you. So we have another item here. So I represent the Institute for this small gifts. Yeah, photo taking.
Thank you.
Yeah. That's a post for the. Okay.